We're here with Frank Marks, Director of NOAA's Hurricane Research Division and the 2011 recipient of the Verner Suomi Award. Congratulations.
Thank you.
This award recognizes highly significant technological achievement in the atmospheric-related oceanic and hydrologic sciences. You received the award for using airborne Doppler radar and other instrumentation to better understand the inner workings of tropical cyclones. Can you tell us about your research, what it entailed, and what you learned?
The Doppler radar has been around for a long time. Many people know of it, they hear of it on the news all the time, but it's actually been around since the mid-60s. One of my mentors and good friend, Dave Atlas, brought a scientist over from France named Roger Lamitte, who brought the idea of the Doppler radar. They'd been using it in France, and he set it up in the Boston area with the Air Force Research Laboratory. Roger was a quite inventive guy, and the way Doppler works is you send out a pulse of energy, and then you receive the pulse coming back, but the pulse is slightly shifted because the particles that it intercepts are moving. So that shift you can detect. And the first receivers they had were audio. They would sit there and they'd listen to the as the sound of as the sweep went around, that they'd hear that. Now Roger also came up with the idea. After he left Air Force Research, he went to NOAA, out to the Boulder laboratories, and he developed a concept for what he called an airborne Doppler radar. It would be a Doppler radar that would mount on a plane that could then, as you fly. One of the problems with radars is that things that are far away, the way the beam works, the geometry of the Earth is curved, you're looking up higher and higher in space, so you have to wait for things to come to you. Roger's idea, brilliant idea, was to take an airplane and then go to where you wanted to sample. You don't have to wait. So he came up with this idea in 1971. In 1980, when I arrived at Miami, we had a radar system on the P-3s, which are the two NOAA research aircraft that they've had since 1973, that we used to fly into hurricanes. These radars were not Dopplerized. They could measure the power coming back, which was related to the strength of the rain, but it couldn't measure the movement. So in 1983, we worked with NSSL, the National Severe Storms Laboratory, another NOAA lab, to implement Roger's idea on the P-3s. They built a Doppler receiver so that we could sense the movement of the particles. We put it on as a separate system on the aircraft. We routed the radar signal to two receivers, one to get the power and one to get the Doppler. And in '83, we flew it for the first time in a winter storm off New England. And then the first hurricane was in 1984, Hurricane Debbie. And Bob Howes, another good friend of mine who lives here in Seattle, and I took that data and started to see what we could do with it. And that's just when it just grew. We had a cover of the Bulletin in 1984 showing images of the Debbie Doppler. And I'll never forget Bob, who was a good friend of mine. He said, "Are you sure this is working right? These don't look right." Because we saw, we expected to see the swirling motion of the hurricane. But because the way the Doppler radar works is the plane flies, you're doing like a CAT scan through the storm. So you're not looking at one level, you're sweeping forward and aft as you fly, and you're making cross sections. And so as you fly, you have to turn. In those days, we'd have to turn to get another look, a different angle. And then I wrote software that would then put that together to make a 3D wind field. And the problem was, when Bob and I were looking at the analyses, we saw the swirling motion of the hurricane, but then we saw something that looked like a little swirl that wasn't part of the hurricane. And we were puzzled by that. And of course, that grew into a lot of other things, but of course it was a test of our software. Every time I change it, Bob would say, "Is it still there?" Because we thought it was an aberration. But all of a sudden we're starting to see details of the structure of the storm that we could only imagine, because in those days, the structure of the storm was based on multiple aircraft penetrations at different heights, and you would have to assume the storm was stationary over a long time because the plane would take time, or if you had multiple planes. It was very costly and time-consuming, and then you really only got a mean structure, an axisymmetric or an azimuthal mean around the center. And so we were seeing, wind fields and streaks of wind, stronger wind, and they had three-dimensional structure. And then in 1987, we were flying in Alicia, and Bob and I again were collaborating, and I had this idea that I could use, because the way the radar scans, it goes through the vertical plane, every time it goes around. And of course, one of the hard things to get from a Doppler radar is vertical velocity, because you're usually looking horizontally. The radar scans horizontally, and then you have to do some kind of an analysis to get the vertical winds out. And you have to make some assumptions about continuity or the boundary conditions, whether it's zero at the ground, but of course you never saw the ground. So here we have this vertical cross-section and a vertical profile. And we came up with a way, I developed a technique where we could retrieve the vertical wind directly as a direct look up and down. Now, we had to correct the beam geometry and stuff. And of course, that's grown, and then the next step was to try and do operational analysis, something we could give the hurricanes. So what? We're learning stuff about the structure. The next step was, how do we get that into the hands of the hurricane specialists? And so we had to develop all this technology, all the analysis techniques. It would take us, I think in the beginning it took us about 2 years of doing analysis. You know, and we refined it and refined it and refined it. And eventually we got it to the point where we were trying to do single pass analyses, and we came up, I worked with Wen-Chao Lee at NCAR on when he was a postdoc, working with Rick Carbone and I, we came up with this thing called velocity track display. So as the plane flies, you're looking across, and you can take advantage of that because the wind's going one way on one side and one way on the other side, and it's zero in the middle, so you can estimate the circulation. And so we could do that analysis. And now we've evolved it to the point where I'm working with my colleague John Gamache, who developed this really nice three-dimensional analysis software that evolved from what we developed. And now we do all the quality control on the plane. We have the satellite communications on the aircraft to pump the data down to the ground in real time, put it into a numerical model, add it to the analysis to improve the analysis of the model runs, and pump it through. And we can do that in the research mode right now in real time. And we're working towards putting that through for operations, to do it in the numerical models operationally in the next year or two. So I mean, that's kind of in a nutshell my evolution through the whole problem.
That is impressive, and that came about in the last. That was a slowly, but then eventually ramped up 30-year period.
Yeah, well,
the technology has abounded during that time.
The technology the radar technology has not changed so much. The computing power has changed a lot. The telecommunications has improved. I mean, the first time we sent data off in real-time Doppler analyses in real time was like 1988, 1989. But the problem was the telecommunications, we had a very narrow bandwidth of information we could pump through the satellites. So it was we had to reduce the data, shrink it, and we really could only send pictures. And then now we're at the point where we have almost the equivalent of 400 kilobaud modem, which is not a lot when you think about the terabyte speed we talk about in telecommunications these days. But through the satellite, that's a lot. And we have 2 of them on the plane, and we have a whole workstation which actually runs on a laptop now. It used to be a big computer with a big screen. Now we just have a laptop that plugs in, and the data flow goes right into the laptop, and you can do everything there. So you see that evolution of the technology. Now, the thing that has changed a lot, though, is our approach. My goal always was to try and improve our understanding of the hurricane, but now, in the last 10 years, it's been, how do I improve the model? How do I improve the forecast? How do I get better guidance? How do I get a better initial condition? And so we've been moving more from a technology development to a software quality control, making it as bulletproof as possible so it can run operationally. Every time the plane flies, the data just flows. Now, we were able to achieve that for the first time all the way through from the aircraft to the NCEP Central Operations Computer in Tomas last year. That was it. I mean, all the pieces finally came together. We've been testing different parts of the plumbing, and of course everything breaks, and you fix it, and you break it, and fix it, and it's just been a joy to watch. But it's been, gnashing of teeth trying to get to the point where you can actually say, I got it, it works.
Now, you've been with the Hurricane Research Division since you began your career in 1980.
Correct.
What got you started in this facet of meteorology? Why Doppler radar and that technology versus some other area?
This comes into where I get into my serendipity. I'm a strong believer in serendipity. you put yourself into positions where good can happen. There's more to life than what you learn as a scientist. There's how you interact with people and how you look at problems. If you're open to change and if you're open to new ideas, when opportunity knocks, you naturally just take it, and that's what serendipity is all about. I was fortunate enough to be a grad student at MIT in the late mid-70s during the GATE experiment, which was the GARP, Atlantic Tropical Experiment. GARP stood for the Global Atmospheric Research Program, just this huge WMO-sponsored program. I was a first-year graduate student. I put in my application for a UCAR, University Corporation Atmospheric Research Scholarship, to go to Africa for 3 months and work on the GATE program. And they were going to put me on a ship. And they were only going to take 30 graduate students. I put in my name. I was an alternate. They picked 32 of us. I was the alternate. So my job was to sit in Dakar, Senegal, for 100 days, in case somebody got sick or somebody got hurt, and then I would fill in. Now, fortunately for me, nothing ever happened. I stayed in Dakar the whole time. I got to meet all these luminaries in my field and got to make some very good friends and close collaborators who became mentors eventually. Ed Zipser, Bob Burpee, Noel Lesueur, Dick Reed, I mean, you name it. Who's who of tropical meteorology, Bill Gray. It was just a phenomenal experience. The first year graduate student have a window. I met Vern Sumi for the first time there. And Vern was a character. He was, I'd like to think I was just the way he was, but he was just something else. And I'm so honored to have won the award named after him because, I was a first-year graduate student, and, he was not quite, a superstar, but to me he was something special. And he said to me, I remember, because I was there interpreting radar data, because I worked at MIT's radar lab for Polly Austin and Speedy Otis, and they were arguing about the radars because they were having a problem in GATE that they had first started to use these nav-aid radio sounds, and the nav-aid radio sounds were giving strange winds when they compared to the ones where you tracked them with the radar, the way the Russians were doing. So my job was to compare the Russian ship radar, the balloon soundings to the American nav-aid soundings, and we were finding problems. And I remember being in the meeting, and Vern was in the back, and we were talking about the radars. Oh, we got to do the radar. And Vern stood up and he said, "We should use the radars to track the balloons. What do we need radars for to tell us it's raining? When it gets dark, it rains." And that's the kind of guy Vern was. That was pronouncement. Of course, he didn't win out. We kept the radars there. But that's where I got experience in the big field programs and working with radars. And I got to meet a good friend, Bob Burpee, who became my mentor. And when I was finishing up MIT, he was on a year sabbatical. And he said, we're looking for somebody at the Hurricane Research Laboratory. It was then called the NOAA National Hurricane Research Laboratory. And he said, well, why don't you come down and interview? And I came down and I met Stan Rosenthal, who was the director at the time, and gave a seminar, and next thing I know, I'm offered a position. Now, I'd done tropical meteorology. I mean, I had also done winter weather, coastal fronts, worked with Lance Bozart, Fred Sanders. But once I had gone to Dakar, the tropics, I knew I was a tropical person. It had to be tropics. But I never thought tropical cyclones or hurricanes would be my field until Bob said, hey, apply. Next thing I know, a year later, I graduated. I'm in Miami at the Hurricane Research Division, or what became the Hurricane Research Division. Flying in airplanes and hurricanes. I mean, the first summer I was there, I flew into Hurricane Allen. That was my first experience. I was hooked. It was an easy one.
I was just going to say that.
I was hooked, big time.
Now that you've gone through this evolution in the technology over these decades now, what do you wish you had in your arsenal, or that you could manipulate this radar data with, or maybe some other technology, and why?
I think, technology always evolves. I've done 2 review articles on how radar has affected tropical cyclone or studies of the tropics. And each time I put in a chapter on technology, because technology marches forward. Technology is always changing. I would say that the thing that I'm looking at now is, I know the limitations. I've worked with Doppler Radar long enough to know its strengths and its limitations. It is a wonderful tool. It gives us a lot of ability to provide better analysis. Two areas that I think we need to put a lot of effort into. One is how to use the Doppler to improve the numerical models. A lot of people are working in the data assimilation field to try and bring the Doppler Radar data in. And I view myself and the Doppler Radar community has to be right up there with them in full partnership to make this work. And I've dedicated, whatever I got left to put into that and to make that happen for the hurricane problem, because I viewed that. The second thing, though, on the technology side, is Doppler Lidar. The beauty of the Doppler Lidar, if you work it like a Doppler radar, and there's two different types of Doppler lidars. The one I'm thinking about is what they call coherent, which means it sends out a pulse of light and measures the backscatter and the motion. It looks at the shift in the visible frequency off of aerosol and precipitation particles or cloud particles in the beam. It is a perfect complement. One of the big problems with Doppler radar is you only get winds where there's rain or there's precipitation particles, depending on the wavelength of the radar. I mean, we've worked with everything from up to 90 gigahertz, which is the W band, which are really, really tiny wavelengths. So you can look into cloud particles. But I'm really looking forward to Doppler lidars coming aboard. We're going to put one on the P3 this summer and fly it in tandem. And what I'm hoping for is when we're flying through a hurricane, no matter whether it's clear or not raining or it's raining, I'm going to get winds and I'm going to get the full structure of the wind field. Now, if I had my druthers, the only other thing I'd love is a sensor that would give me the humidity and the thermodynamics at the same resolution and scale, which I don't know how to do yet. Vern probably came closest to doing that with his satellite, his spin scan satellite microwave imager that he developed when he was doing his technology developments. But I view that I've just been fortunate, to be able to be alive at a time when you can take advantage of this type of stuff. And one thing I want to say is to the students, take time to think about and be open to new ideas. You don't learn everything in a book. You can learn how to do things from, how things work and how to do them, but you don't know how to do them until you try it. And just think out of the box. Be willing to look at things with a different perspective, and you will have a wonderful career. Serendipity will find you, and you will do well.
Now, I'm going to ask one more question. Step outside your professional self for a moment, and I want to ask you, when you first learned that you're going to receive this award, what was your reaction?
Let me tell you, I was flummoxed. I don't know if that's a proper term, but I was, I'm not usually at a loss for words, but when Peggy Lamone, who is the president and a good friend, called me, she left a voicemail and said, "Frank, we got to talk." And I hadn't heard from Peggy in like years. She used to fly with us, and we used to do a lot of research together. She was involved in GATE as a very young postdoc when I was a student. So I've known her since I've been doing this stuff. And we're good friends. And so I hadn't heard from her in a long time. And so when she left a voicemail on my machine, I'm thinking, what does Peggy want? And so we finally connected. It was in the middle of September. And she said, "Frank, I got some good news for you." And I said, "What?" She said, "You just won the Verner Award." And I said, "What?" I said, "Which one is that?" I was a little bit, I was like being poleaxed. Is the best thing you can say. I had no knowledge of ever being nominated. I didn't know whether anything I'd ever done was noticed by people who, besides myself and my good friends and colleagues. And so to me, it's been a fantastic honor. I mean, I am getting speechless again. It's incredible, to say the least.
Well, thank you very much for the interview, and congratulations again.
Thank you, Chris. It's been a pleasure.